So I have to present my paper, which is sustainable AI. The main core concept is to make the training process of machine learning algorithms or AI algorithms more sustainable and more carbon efficient. So here is the outline of my presentation. I will start with the motivation, and then I will discuss a few problems with the standard back propagation, which is the main bottleneck where mostly calculations or flops are occurred. Then I present a proposed solution and the algorithm of the proposed solution and the key contributions of my paper, and then I will discuss the results and the training time and utilization. And at last, I will discuss about the trade-off analysis between and the deployment strategy, and I will conclude my presentation then. So the motivation is basically, as we know, the deep learning models boost autonomy in medicine and agriculture, but are compute and carbon intensive. So the edge devices demand real-time inference and restrict power and memory limits. So we have seen like the training state-of-the-art models required 300,000 increase extra time increase in compute from that era from 2012 to 2018, and there's significant carbon emission if we train one NLP model, which has a 5 times greater lifetime emission of an average car. So here there is a rise of a green AI. So people work towards the more efficient AI system rather than make it more accurate. Uh, make it more accurate. So the focus shifted towards the computational efficiency and carbon footprint as a key metrics alongside the accuracy. So it has the benefits around in the environmental and has very lower financial barriers and also increase the inclusivity. So my focus in this paper is to make the training process efficient and especially make it on device. And I will discuss the device which I've used in with like a sparse backpropagation method. So with this problem with the standard backpropagations are like in the training the deep neural network, it's very computational intensive. So it has to update a vast number of parameters in every iteration, a very dense updates. So there is inefficiency in if we go towards the deep neural network in which this backpropagation occur, in which it calculates the gradient for all weights, and many weights update might be very small and very unimportant for the final accuracy. So there is a considerable computation is redundant. So our objective is to reduce that computational workload and energy consumption during training, and achieve this by making back propagation sparse. Like we can drop those redundant weights. So the main challenge is to maintain the model accuracy for avoiding increasing training accuracy significantly. So the proposed solution is a back propagation. The the main concept is to compute and apply only a small subset of a weight gradients in each iteration. Like you can choose the top k largest gradients and update that in each iteration rather than update whole weights. So the previous works was saying like updating 1 to 4% of weight can train model to full accuracy, potentially reducing accuracy. So in my paper, I have leverage this concept for make it more energy efficient and make it on-device learning. So what's the advantage is it give you a data privacy because it's on a device like it's on the edge and you don't need to share your data. So if and it also decrease the latency and also avoid that cloud data transfer. So yeah, the challenges are still there for like if you there's limited power budgets and hardware. So this is the main methodology like in uh, general machine learning model, like how they train, like if there is a forward path and then there is a backward path in which all the gradients are computed. But here we can just take the cell subset which is based on the largest gradient value, and we then for just those update those values for that layers and per layer, like it is calculated like the key value is calculated by the layer wise, and we can just only update those gradient and then drop the redundant gradient and make the training process efficient. So the key contribution was like we trained it on device like these four models in which I have used like the two big models and the two small models, and then apply the gradient classification. The setup I was used the NVIDIA Jetson AGX Orin, and I have the integrated the CodeCarbon library for measurement of energy and carbon emission. So I've taken the vision datasets like Cypher 10 and Cypher 100 and Power 102, and then I have uh, applied the backpropagation with standard dense training and calculate the accuracy loss and energy consumption. So there is a trade-off analysis between the accuracy and carbon computation efficiency versus sustainability, like how is accurate if we can drop the gradients, and how it may computationally efficient and sustainable training process. Then I've seen that my results are like 30 to 40% energy to carbon reduction with a minimal accuracy expect, and then there is how it can be deployed on device learning in certain in different applications. We can see like here is the main results for me for my experiments, like accuracy impact for like if we can go towards the 10% sparse update. So there's a like minimal of a less than 1% of accuracy drop, versus full dense baseline across model, and sometimes it gets slightly better due to regularization effect. We have seen in ResNet 18 on Flower 102 dataset, and we seen like in energy and energy and emission savings on ResNet 18 to up to like 25 to 28% energy reduction. And in dense 121 mol, it's up to 134 percent energy cut. Similarly, on the mobile being equivalent to it's almost 19% saving. And the average CO2 drop is around 25 to 35%, depending like on the model, like which model I've seen, like up to 25 to 35%. And we've seen like epoch time reduced by uh, be like almost 20 to 30%, and like we have used a small GPU, so it is faster, like not really faster, but it will be sustainable and more good for more go towards where toward those applications where the latency is very meaningful. But Sparse Backbone offers a low complexity and hardware agnostic way to enable train AI on edge devices. So if we see the training time and utilization in dense one-to-one on Cipher 100, it's like almost to 1 second for per epoch in dense way. But in like sparse propagation, it reduced to 0.75 like 28% of a speed up in Breslin 18 is like 22% speed up that indicate the GPU could leverage reduced automatic operation. So that in if we see the in dense training, we can see the GPU nearly near 99% utilization during backprobe, and but if we see the it drop to 70 to 80% during reading masking. So like slightly lower average GPU utilization over for sparse. So GPU spend more time idle between batches and finished quickly. So there is some trade-off analysis like accuracy and energy trade-off. Like some can use the sparse delay based on the acceptable accuracy drop, and also depend on the application and the data set as well. Like I've used a very small data set, but it depend on the data set how it work on the large, more complicated data set. So, and what is the threshold to how much you can bear for the accuracy drop? So we can see like a 1% accuracy drop for 30% of it energy saving with 10% of update. So, like sparsity can act as a regularizer, sometime improving accuracy on small data set. But yeah, it has to be tested on a larger data set, and it is our goal in future as well. So we can use the hybrid approach like sparse for most epoch, then switch to the dense for final fine tuning. So, like we can deploy these strategies where accuracy is also important, and like we can use like gradually change this positive level during training. There are certain ways. So yeah, and like on device, we can see like the battery life, the thermal limits of the device, and how it can sparse back propagation helps the to reduce that to power draw and total energy, and like performance and lower precision, like in 8-bit, like and even more quantized, more like for 4-bit and for a single bit and binary precision, how it can work on that. And if it work on that as well, like it will reduce more time and more efficient if we can go towards a more quantized model. And then we can see like how it can, like I talked about like a model compression, how it works with the pruning layers and with the quantization for further saving. And like, yeah, for deployment, you can so rely on purely edge models or a cloud edge based model, and how it reduces the need for our cloud retaining and data energy costs. So yeah, summary for my findings like 5 to 8%, 10% weight updates, maintain the accuracy within the 1 to 2% for CNN target training and vision tasks, and achieve significant energy saving of up to 20 to 35% and corresponding carbon emission reduction. So there's impact of on green AI, like produce a practical technique to reduce energy usage, highlights the existence of substantial redundancy in neural network training and crucial for the growing field of the AI at the edge and continual learning. So this was the main like a base of our work. We are basically working on the training of a large language model or fine tuning of a large language model based on these devices. So it wasn't just beginning of our work, like how it can, we can see if we can fine tune a large language model on the device for a specific application. So yeah, the work is going on basically on that side, where we can use the hybrid approach, where like we'll use some sparse backpropagation with a quantized model. So yeah, here the work is basically going on. Thank you.
Okay. Okay. Thanks, Hassan. Very interesting, Hassan. Could I ask you just one or two questions?
Yeah, yeah.
Yeah, thanks. What's the spec on the Jetson? I mean, how many cores does it have in GPUs? What's the spec on that? Can you give me details on that?
Specs, it's a 64 GB RAM. So it was a high, like a top model of Jetson. It it can be act as well like a big GPU, yeah. Because I trained the full model on that as well. Like it take me time, and it's very handy. Like we can use those PyTorch model on that as well. Like yeah.
Okay. And how large was the data set you used to train it? In the data sets, what was their size in gigabytes or whatever?
Like certain like the specific cipher 10 and cipher 100, it's I guess I don't remember the size, but it is considered to be slightly moderate kind of a size of that
Yeah, I
data
was
set.
just asking in relation to how representative is the data set compared to, NLP data sets that you would use, to train, a neural network in practice.
Yeah. For the NLP or for like large language model, like we can not use a bigger data set. We will use some chunks of the data set, like or we can fine tune on certain level of application. So we cannot use for a whole. We cannot train the whole model for the NLP, whole NLP LLMs, but whether it was like a bird, like it was a basic word, or
Mm,
we cannot train it on a device. Yeah. So yeah, it is like we can on not only use this back propagation sparse back only. We have to be use the quantized model, or we have to be that as well. Like we give some level to words like binary more like where it is like a 0 or 1. So yeah, we are experimenting on that, like but in start the accuracy drop was high, but we can use use a different kind of a concept, like if you know about the LoRa updates, which in which just few updates are sending to which is like which have to be only update few rather than whole model on the fine tuning. Yeah.
okay. And when you were measuring the energy consumption, were you using an onboard application, or were you measuring it like through a meter? How were you
Yeah,
calculating energy
yeah,
consumed?
it's a PyTorch library which is CodeCarbon. It's CodeCarbon API. It's used your machine whole specs which are you using for training, and they have their statistics to how to calculate those emission based. Like yeah, it's not like that accurate, but they are using like most like relative to that, like how it will really work. Yeah.
Is it
But
based
yeah,
on, does it analyze like the instructions that you're executing and the power
yeah,
per
yeah.
instruction?
It's
Okay.
an API. We install the API. It can take your machine whole information, which machine are you using for the training. So it will take those specs in the mind and the time which it take for whole, and it can estimate the carbon emission, like it can take it.
Okay. And how accurate do they say it is? Is it like 5, 10, 15%? Because like some onboard a sort of APIs like on various Dell machines, they could be 30% inaccurate. Some of the the power figures or numbers that the software gives you. Is any indication of just how accurate the energy calculation is for using that particular tool? Is there any details on that at all?
We didn't experiment on that, but there is an idea to like we can install like the if we have to experiment on the like a device I have in the lab, so we can install a meter for that, like, and we see how much it consumption here there,
For
and
reality. Yeah.
then we can compare it with the CodeCarbon library, and here we can also then we can that comparison we can take towards the cloud as well. Like if we cannot compare the we cannot calculate the cloud consumption from here, but we
But
can
it's
take
still
a
possible. Yeah.
yeah, but we can take a relative comparison from this because we have that device. Like we can see like that much factor is lacking, like how much it can be. So yeah, it can
Okay.
be used like that as well, like from uh, practical meter.
Yeah. Okay, thanks very much, Hassan. Very interesting. I would say I haven't read your paper, but yet I'm reading all of them. There's a lot to read, but it's one I have particular interest in looking at the energy consumption of servers in sort of cloud environments and how to manage that. So I'll have a particular interest in reading your paper, and your presentation was very interesting. So thanks for that, Hassan.
Thank you so much. Thanks so much.
Yeah. Okay. Be in contact. All the best, Hassan. Bye.
Thank you. Bye.